Welcome everyone to this 8th webinar in the series of webinars in the EO4SD-FM project. And today our topic will be mangrove area change and recovery. And here we have our presentation team. So we have here Andy Dean from Hatfield Consultants. He's a remote sensing and geomatics director there. Then we have Marcos Kavlin, also from Hatfield, remote sensing specialist. And lastly, Victor Tang from Hatfield, also a remote sensing specialist. And before we start, a couple of housekeeping issues. So we will have a question and answer session at the end of the webinar. And during the webinar, you can type your questions in the chat. And this session will be recorded. So if you have to perhaps leave early, you will be able to access the link for the recording, and it will be shared with you soon after the webinar. And as default, all of your microphones and cameras should be turned off, but if they aren't, please turn them off for the duration of the webinar. And without further ado, I'll be giving the floor off to Andy Dean. So we can start the actual presentation.
Thank you, Saya. So the context of this webinar, as Saya mentioned, is the Earth Observation for Sustainable Development Initiative from ESA, specifically the forest management theme. And the objective of this project, which has been running for about 2.5 years, was to engage with international finance institutions and their partners to demonstrate the benefits of satellite Earth observation technology for forest management in this case, and mangrove was one of the themes under forest management. The finance institutions of the World Bank and the Asian Development Bank in this case, and the overall activities were related to working closely with one of those institutions, their government partners, to demonstrate the benefits of using satellite Earth observation products analysis to help inform their projects. As part of the project, we've had a series of webinars. This is the second to last webinar on mangrove mapping. There's one more coming up next week on land use, land cover mapping. So if you're interested, you can find the link to sign up for that webinar on the EO4SD Forest Info website. Here you can also find all of the links to the previous webinars, the recordings, and you can find them there. Other interesting and useful information is on the website. There's some blog posts, some stories, story maps about some of the work that we've done. Here's one example from some deforestation monitoring work that was completed, and there is a story about some of the mangrove work that we've done on the website. So the mangrove presentation today, our objective is to just make sure that we're communicating what mangrove products did we generate, what work did we do, specifically 2 use cases with the Asian Development Bank and the World Bank and their clients and partners. One was in Fiji with the government of Fiji, and one is still ongoing, wrapping up with Indonesia and the World Bank. The products from the portfolio that we defined for the EO4SD-FM project is mangrove extent and change, but also mangrove condition and change. So a few mangrove products are part of the work that we've done, different products which we will introduce in a moment. But first, I think we'll have a quick poll for the participants in the webinar.
That's correct. If you would please answer whether or not you've used a mangrove classification product, such as Global Mangrove Watch, in the past.
Okay, everyone has used a mangrove classification product. Almost everyone has used a mangrove classification product.
Interesting.
Okay,
Thank
maybe
you.
about 80%. That's good. Good to know.
A good amount. And I suppose we also would like to know how you would rank the following products based on your interest in them.
Okay, lots of interest in annual mangrove extent, which is obviously similar to Global Mangrove Watch and some of the work that we've done, and some other attributes related to mangrove characteristics, and some interest in carbon stock, but probably interest in all of the products, I would imagine. So with that, we'll dive into a quick explainer on the products before we get to the use cases. So the products that we've been generating are primarily being produced using Sentinel-1 and Sentinel-2 data, which means that we can produce products at 10-meter spatial resolution. The temporal availability is roughly annual from 2017 to present. Sentinel-2 was launched a bit earlier than that, but the image availability cloud cover challenges means that realistically 2017 is a good year to start producing these products. And there's some flexibility in the product that, obviously the projection, the eventual ultimate definition of mangrove forest, minimum mapping unit, canopy cover could be adjusted to a national preference. And the format is obviously flexible depending on how people want to receive the data. We've defined mangrove as extent as a key product, but we also will produce a coastal tree cover product as well, because often mangrove and coastal tree cover are obviously found in the same areas. And there's that transition from mangrove to terrestrial tree cover, and coastal trees in general provide good benefits for coastal resilience and coastal protection. So both products can be generated with a specific layer on mangrove. We also produce a mangrove condition or density product. That's based on a fairly simple approach using vegetation indices. With the data that we generate on an annual basis, we can produce mangrove gain and loss data and change in mangrove condition. In other words, the trajectory of that vegetation index that shows whether the mangrove is relatively dense or not. Other useful layers could be the probability of mangrove within that coastal tree cover area. So the models that we use can generate essentially a probability. So you can see how confident is the prediction of mangrove in a particular area. This is a visual overview of the workflow. So the primary input is Sentinel-2, Sentinel-1 images. We have to address the cloud cover in Sentinel-2 images through compositing. to create a cloud-free composite. We can bring in terrain attributes, slope, for example, using the Copernicus digital elevation model. From both the radar and the optical data, we calculate a range of indices as inputs to a model. So vegetation indices like NDVI and NBR, and some radar indices such as cross-polarization ratios. We build label training data through visual interpretation. We'll go into a bit more detail. The modeling approach that we've chosen is to use random forest with an 80-20 training validation split, so that we can complete independent validation. We know that there are more sophisticated modeling approaches out there, but random forest is widely adopted and gives us a better opportunity with capacity building or training if we're using a modeling approach like random forest. For the labeling, this is the case in Fiji. We actually used the Planet NICFI high-resolution base maps that are freely available biannually and then monthly since 2017 to present, or monthly more recently. So we created the labeling through standard approach, stratified random sampling across mangrove and non-mangrove classes. You can see the distribution for the two main islands of Fiji here. And we did provide an interpretation guide to the analysts for performing the labeling in an effort to ensure a high level of consistency in the labels. There are some existing training data sets available. Some of you may be familiar with this Coast Train data set, but we completed the labeling ourselves. And in Indonesia, actually, the government partner participated in the labeling process, which was quite good to see. In terms of production, this is the challenging part. We're working with big data, obviously. Sentinel-1 and Sentinel-2 images. We need to composite them. We need to calculate indices and then work with them and produce a classification using the machine learning model. So, as you might expect, we worked in a cloud platform to conduct the work. The platform that we used was the Planetary Computer from Microsoft, which provides access to all the Sentinel data in the cloud. So both Sentinel-1 and Sentinel-2. The Sentinel-2 data are already calibrated to surface reflectance to level 2. So that is a helpful step that's already completed. We obtained the coastlines data from the World Bank catalog. The NICFI data from Planet, that's available as a web service. It's also available directly in the Planetary Computer if you are registered with the Planet NICFI initiative. We completed the classification workflow and developed a series of Jupyter notebooks to help us to do that. You can see a few screenshots on the right. This type of approach may be familiar to lots of people. Lots of people who are working with remote sensing data in the cloud or locally, building your workflow using a Jupyter notebook. So the basic steps that we were able to do are things like collecting the Sentinel-1 and 2 images only within the AOI that we're working with, the area of interest, completing the image composition, the cloud-free composition of Sentinel-2 data, calculating those spectral indices from the Sentinel-1 and Sentinel-2 data, the terrain attributes from the Copernicus DEM, and then having trained the model, we can predict the mangrove extent with the random forest model, all within these Jupyter notebooks. And that just helps different analysts to use this workflow, repeat the workflow from Fiji to Indonesia in this case. In terms of validation, we're going to show the use cases in Fiji and Indonesia next, but this is just to give you a general sense of the accuracy of the products. I think most people would agree that Global Mangrove Watch is the global standard for mangrove products. It's got a long history, and initially using ALOS radar data, generating products 25-meter resolution. We know that Global Mangrove Watch is moving to a 10-meter Sentinel-2 based product, and they have a draft 2020 baseline that will be released. So we will evaluate our products against the final version of that 2020 Global Mangrove Watch product. But at the moment, what we were able to do is compare against the 25-meter product in 2020. And the example on the screen here is 2017, sorry. We were also able to use the independent reference data to conduct an accuracy assessment. And in Fiji, we've received a very high overall accuracy, 97%. And the other statistic there, that kappa statistic, is 0.94, which indicates a very strong classification performance. And that's what we would expect. We know that mapping mangrove is a feasible and typically highly accurate product that we can generate. So good confidence in the products. Now we're going to introduce the two use cases. We're going to also show a couple of the other products like mangrove condition and how useful that was as part of the use cases. So the first use case is in Fiji, and it was related to a project related to coastal resilience and nature-based and integrated solutions. So the Asian Development Bank was working with the government of Fiji to help them address some of those climate-related challenges. And the intent is to implement a mix of green and grey infrastructure, so to help protect coastal communities from climate change impacts. There were potential sites across the two main islands, and the site selection and planning needed to be informed by good information on mangrove extent and condition and change. The challenges that we faced was that there were numerous sites all across these islands being evaluated. It's a large area. The site selection process was dynamic, so candidate sites were being considered and new sites were coming up. So we needed to have landscape level information, but then when a site was under serious consideration, to have site-specific, site-level information. So our solution was to produce a consistent mangrove product for the entire coastline of these two main islands for 2017, every year from 2017 to 2022, so that we could produce on-demand mapping of mangrove status and gain for candidate landscapes, and then when necessary, do the detailed site level mapping. So these are fairly large areas that we mapped for 5 years. VT is 10,000 square kilometers with more than 1,000 meters of 1,000 kilometers of coastline, and Vanua is 5,000 square kilometers with 1,300 kilometers of coastline. So using Sentinel-2, we mapped a large area for over multiple years. What that enabled us to do is when a candidate landscape was being considered, we were able to produce maps and products such as the one that's on the screen, and I'll try to explain this product. So this is Namarai village area. Within the box is the real sort of focus area. And what we did is we mapped the mangrove extent from 2017 to 2022. And what you can see here is the color scheme means areas of stable mangrove, areas of mangrove gain, and areas of mangrove loss. We don't actually have any areas of mangrove loss in this area, but we were quite surprised when we generated this product to see areas of mangrove gain. We thought maybe there's a problem with one of our models. We wanted to investigate it a little bit further, but we shared the results with the Asian Development Bank and their partner, and we investigated a bit further. But we were actually quite convinced that our product is correct, and what we were seeing here is essentially mangrove gain. One thing we did is we used this mangrove condition product approach to look at the change in the vegetation index between 2017 and 2022. And what we could see is a clear increase in the vegetation index, which indicates an increase in mangrove density. So the yellow colors mean that the vegetation index was relatively stable. The green means that the index has been increasing and the density of mangrove has increased. So this gave us some more confidence that what we were seeing here was actually an increase in the density of mangrove in this example. And in fact, when we supported the Asian Development Bank with some detailed site level mapping, and we resolution data for a small snapshot, we found that these data sets supported the evidence that Sentinel-2 had provided. So you can see in 2015 in the upper left, a very good-looking mangrove condition. In the 2017 image that was taken after the impact of a tropical storm, you can actually see that there was quite a lot of damage and degradation of the mangrove in this area around this village. But in 2021, which is the most recent very high resolution data we could obtain, we could see that the mangrove has started to recover. So what you can see is that our Sentinel-2 product from 2017 to 2022 was identifying areas where the mangrove was resilient, the mangrove had started to recover. And this type of information was quite informative for the Asian Development Bank and the government of Fiji to plan their nature-based seawall investments and to understand the changes and dynamics that had happened in this area, prior to their efforts to improve the protection and resilience for this village. And of course, this process could be repeated for multiple villages all across Fiji because we have the Sentinel-2 data product generated. So that's one of the stories, and there is an article on this on the EO4SD Forest Management website. Use case 2 is in Indonesia. This work is still ongoing. We're just wrapping it up. But the project that we supported here was with the World Bank and the government of Indonesia's Mangrove and Peatland Restoration Agency, and a particular project called Mangroves for Coastal Resilience. So in Indonesia, mangroves they have some of the most extensive mangrove ecosystems in the world, and some of the most important, but they have been threatened by deforestation, unsustainable use, conversion to aquaculture, and more recently oil palm plantations. So the government of Indonesia, with the support of the World Bank, has a national mangrove rehabilitation program to rehabilitate more than 600,000 hectares of degraded mangrove. And so the M4CR project aims to support that process with a range of initiatives. One component of that project is related to strengthening the policies and institutions for mangrove management and to help with financing of mangrove restoration. And one subcomponent of that's really interesting to us, of course, is a process to improve and update the national mangrove mapping. So we wanted to demonstrate, again, Sentinel-1 and Sentinel-2 using the same or similar approach that we just introduced before, the Fiji use case. The particular challenges with the work in Indonesia is that the priority provinces were Eastern North Kalimantan on the island of Borneo, which is a very large coastal area. It has quite dynamic land use. There is aquaculture, there is coastal plantations. The area, especially the Mahakam Delta, is heavily affected by cloud cover. And this is a priority area for BRGM, the Peatland and Mangrove Restoration Agency. So again, a similar approach using the planetary computer and directly involving BRGM in the process, trying to work with them closely on the labeled data collection to produce the models. So the map on the right just confirms this quite large coastal landscape that we want to map. So I would say a large area demonstration. There are other provinces that BRGM want to map, but this is the priority. In this case, we produce similar products. Mangrove tree cover and non-mangrove tree cover. So we wanted to map all coastal tree cover and specifically then the mangrove tree cover. We want to map mangrove condition again and the changing condition using a vegetation index. And again, a useful layer can be the probability of mangrove within that coastal tree cover area, just as an information layer to help understand that there is some uncertainty in whether an area is mangrove, especially when you get into that transition zone. So here's an example of a Sentinel-2 cloud-free composite for part of Indonesia. This is a part of the Mahakam Delta. So you can see it's quite a complex landscape. This is a famous delta in Indonesia with mangrove that has been affected by aquaculture. You can see the aquaculture in the bottom right. You can see areas of, the green colors indicate mangrove, but there's also some non-mangrove terrestrial forest in this area, and there are actually some plantations. You can see that the compositing process in the Mahakam Delta is very challenging because of cloud cover, and you can see a lot of the river systems with high sediment load. The pixels that get selected in the composite actually are quite variable, but the fact that the river system looks a little bit strange doesn't actually affect the classification of mangrove. We will still be able to accurately map mangrove, non-mangrove, and mangrove condition with composites of this quality. And this is one of the most challenging areas in the world, I think, to make cloud-free composites. So step one is that we predict coastal tree cover. So here's an example of the classification of coastal tree cover with the application of a minimum mapping unit applied as well. So you can see that we're able to map, the extensive areas of tree cover. We're even able to identify with Sentinel-2 some of the narrow strips of tree cover that form along the edges of some of the aquaculture ponds and some of the small patches of tree cover. Within that tree cover area, we're able to identify mangrove, and this is an example of the probability of mangrove data set. So what I should say here is everything that has a color from red to green in this slide is classified as mangrove. The red colors are the areas where the classification of mangrove has the lowest probability. So this is where we say it's mangrove, we think it's mangrove, the model predicts that it's mangrove, but the confidence is lowest. And you can see that makes sense that some of the small patches, the riparian strips of trees or mangrove that have the lowest probability, and that's possibly because the patches are very small. There's some mixing of mangrove with pixels that are water or the aquaculture pond area. So this could just provide an indication of how confident are we that we're correctly predicting mangrove. And here's an example of the mangrove cover and the tree cover combined. So you can see that this can be quite a helpful product in terms of identifying, where do you have tree cover along the coast, which can contribute to resilience in especially in areas that are affected by tropical storms. But we're obviously primarily interested in these very important mangrove ecosystems. So we have the benefit of both in this visualization. Okay, so we've given 2 use cases and introduced the products, the work that we've done. We just want to conclude with a brief summary and some ideas and some of the future work that we've been doing. So I think Global Mangrove Watch demonstrated that it's feasible at large scale to map mangrove extent reliably, and we've demonstrated that we can do it in a very timely manner to support projects and mapping mangrove over large areas. But there are additional mangrove products that are increasingly of interest. Additional biophysical attributes of mangrove, such as canopy closure or the fraction of water and mangrove. So if a mangrove is degraded, as we saw after the 2017 storm in Fiji, potentially the canopy closure product would help to provide some information on the mangrove condition. Canopy height is another useful attribute of the mangrove area. So if we know how high the canopy is, that could help us to understand the condition of the mangrove and potentially some of the different species types that may be present. Those products could be useful inputs into coastal blue carbon initiatives, and we know that estimating carbon stocks above and below ground in mangrove ecosystems is very challenging. But some of these attributes can help to support upscaling of carbon storage estimates. And obviously, these types of attributes could provide additional information for planning and monitoring of mangrove restoration and mangrove management. So if areas that are have a lower canopy closure, lower canopy height, rather than just understanding mangrove extent or general condition from a vegetation index, you could have some more important useful information for management and restoration planning. I just want to close by showing two products that we generated in Madagascar in a different project, but I think that they're quite useful just to illustrate these additional attributes. The first map here is simply a NICFI base map from 2021, so a Planet NICFI base map from 2021. And this project is the Pêche Côtière Durable 2 project, which was in Madagascar and financed by the KfW from Germany, and a collaboration with AHT Group and Madagascar National Parks. In this area, we trained a random forest regression model using JEDI data, which some of you may know about JEDI data. This was applied to Sentinel-1 and Sentinel-2 data. And we found actually that the radar data did provide a good contribution to the model in this case to predict canopy height. And you can see here the color scheme from, low red colors indicate, fairly low canopy height of the mangrove, and, yellow into green colors indicate canopy height getting towards 20 meters. We're still in the process of validating the model, but with JEDI data, you can obviously do that with by holding back some of the data for validation purposes. And then the second product is just the canopy closure, again trained using JEDI, and this shows relatively low to relatively high canopy closure of the mangrove in this area, and this was completed across the entire of Madagascar as an experimental product. And so with that, I'd like to thank everyone for your attention to the presentation. I'm going to hand over to my colleagues who will help to facilitate any questions.